So now we're down to the very last section in 23. We're going to look at the use of the natural log and the Euler's E, and how it applies to RC circuits. Chapter 13 covered the universal time constant curve to determine the charge on a capacitor at some time after power was applied to the circuit. The charge on the capacitor in a series RC circuit then can be calculated by the equation V sub C is equal to E, the applied voltage, multiplied times 1 minus E to the minus T, which is in seconds, and then the product of the resistance in ohms and the capacitance in farads. So these become very, very important when we're dealing with the charge time on a capacitor or an inductor, and the decay time when we allow either of those devices to discharge their energy. So to do this, we have to use this relationship of the natural log, or E, to calculate those. And so we can see from the capacitor voltage relationship, we can derive the resistor relationship as the applied voltage times that E to the minus T over RC directly instead of the difference. And then you can see the last one when a capacitor is discharging. So we're just going to introduce here just a little bit of what goes on in using E for these type relationships. So in this example, we've got a source of 70 volts, we've got a resistor of 680 ohms, and a capacitor at 5 microfarads. And what we're going to do is we're going to close the switch here, and we just want to calculate after a period of time what the charge is going to be on that capacitor. So in this case, we're going to find the voltage drop across the resistor and the capacitor after the switch, 1 microsecond after the switch has closed. So we use that relationship V sub C is equal to the applied voltage multiplied times the difference, 1 minus E to the minus TRC. If we plug in our values of 70 volts for E, 1 microsecond divided by 3.4 times 10 to the minus third, which is the product of 680 and 5 microfarads. And what we get here is a charge or a voltage across the capacitor of 17.8 volts. We can then apply our old standby Kirchhoff's voltage law to calculate then what is left on the resistor. So if we take the difference then of the applied voltage minus that 17.8, we get 52.2 volts across that resistor at that same time period of 1 microsecond. So when you get to your ET132, your AC course, you're going to be doing a lot of this in those sections and calculations. You might even experience it in the DC class toward the end of the course. So anyway, RC circuits and using the E function.